All right, we're going to continue on with this question format. Go ahead and read through the question and pick an answer. This form of energy transfer is convection. Convection is a relatively simple concept. However, it's an extremely complicated mathematical process. Fortunately for us, we don't care about the math, we're just going to focus on a conceptual understanding. The key to convection really goes back to the concept of buoyancy. If we imagine this is a pot of water that we're trying to heat up, the water that's closest to the flame is going to heat up first. As its temperature increases, it becomes less dense, or in other words, more buoyant, and so it will rise. As it does, the cooler water is going to take its place. That cooler water will then heat up and rise and so on and so forth, and then you get this continual process of rising and sinking as water becomes more buoyant or less buoyant depending on its temperature. I found it's easier to gain an appreciation of convection when you can see it visually. Unfortunately, I didn't have time to create my own demonstration, but there's plenty on YouTube. And the bad thing is they're all pretty terrible in quality, but the overall demonstration is actually pretty effective. So let's watch this one. What we're going to see is they're going to dump some hot water on the left, and that's going to be colored red, and some cold water on the right, and that'll be colored blue, and then let's just see the reaction. Okay, you'll notice the red instantly starts to rise back up again, where the blue just hovers at the bottom. And the blue is more dense, so it's going to sink, where the red is less dense, so it's going to want to rise or float. What's interesting is when they start to interact. You can see that there's a clockwise motion that's starting to develop because of the differences in temperature. This is known as convection currents. I want to show one more video of this. This one has better quality, but I actually think the other one has a better demonstration overall. So here they're heating up some water. It's just got some red dye in it. You can see how the hot water is just hovering at the top relative to the cooler water. The other water was cooler. Put a piece of ice in there, so the water right around the ice is going to instantly start cooling off. You can see how that falls because it's now more dense. It's less buoyant. Right, so that combination of hot water rising and cold water sinking is what leads to convection currents. I skipped ahead here. They have another demonstration that's pretty cool to see. So you can see a much more dramatic rising mixing motion. This is sped up 3 times. Here you're seeing surface rise out of the water and then sink down in as well. Okay, I don't know if you're reading down there, but they were talking about ocean currents and tectonic plates. So this is kind of what I was mentioning. Turns out that convection does have a lot to do with the world around us. So ocean currents and tectonic plates are just 2 examples of those. Here's an example on a smaller scale. You may have seen a heater like this at some point in your life. You don't really see them as much anymore, but they used to be really common. There's no fans on this kind of heater. They just have these heating elements that get hot, and they rely on convection to spread the heat around. So the warm air rises, and that leaves a vacancy for the cooler air to rush in and fill. That will heat up and rise, and then you end up getting circulation just due to the convective properties of the air and not a fan. Of course, if you do install a fan on a heater, it actually becomes more efficient at spreading out the energy, but it's not necessarily required for the energy to mix around. Let's go back up and go look at a bigger scale. Here's a picture of our sun. The surface of the sun has a lot of interesting features. It's not just a bland, uniform skin there. If we zoom in on it, this is what we call granulation. It looks granulated, almost looks like popcorn that's popping in the bottom of a pan. That's actually in motion, all of that. We can watch a little clip of that. So as you watch that, it looked very similar to that pot of white fluid that we saw, because we're seeing the same thing. These are convection cells. So the hot fluid is rising out of the center part. That's the brightest part. And as it cools, then it will settle down into these darker areas. Now, those areas aren't actually black and dark like it appears. They're just relatively dimmer than the brightest part in the middle, so they appear black from our perspective. Now, one big difference to that pot of boiling white liquid is that these are actually huge. They look small when we're watching a video like this, but if I give you some sort of comparison, the United States would be about this size. So one of these convection cells is just giant. The sun itself is really mind-blowingly big compared to anything we've ever experienced on Earth. That video mentioned that convection has a lot to do with ocean currents, and that's true, but just weather in general is dominated by convection currents. So it's the motion of fluids, which in this case is air and water, that rising and sinking due to higher temperature, lower temperature is basically what dominates weather patterns. So understanding convection is key to predicting weather and ocean patterns. I want to get back to some questions. Read through this and try to answer it. Okay, the best answer in this case is fluids. It's true that convection works with liquids and it also works with gases, but these are just materials that flow. So anything that flows is called a fluid. So the best answer is fluid rather than gases or liquids individually. Okay, hopefully this one's obvious to you now. I've said this word several times. When you warm up air or you warm up water, it becomes more buoyant. Now for water, we're assuming we're well above the 4 degrees Celsius that we discussed in chapter 15. So we don't have to worry about any of that. You just assume that if the water is warmer, it's more buoyant. If the water is cooler, it's less buoyant. Here's a fun example that kind of combines all this together. This is known as a fire tornado. The mesh around the flame there is circulating the air and it's funneling it into the fire. That's going to feed the fire, so it obviously grows. The air is also guiding the fire. That warm air is going to rise, and so it does. Once we stop the air, you can see that it just dies down and then starts back up again. This is one of the things we miss by not actually meeting together, but the video still does a good job of demonstrating it. Okay, try this question. This one can be a little bit tricky because we warm the air to make it expand, but actually when air expands it tends to cool. Maybe a way to look at that, if I can give you a kind of a simple animation here. So imagine this is just some volume of air, and right now it's restricted to this region. Okay, these little particles are representing the individual motions of the gas molecules. Okay, as I expand that, we've spread out all the molecules, so the molecules are all more spread out. But the more important thing is that when this air was expanding, it had to literally push everything else out of the way because it was surrounded by air, so it had to push that air out of the way. Well, that was work. So the air had to apply a force on the outside air. That force was applied over a distance. That's what we call work, and that's a transfer of energy. In this case, the original volume of gas had lost the energy. It had to do work on the environment to push itself out and make itself bigger. Because it lost energy, its temperature goes down. That's what's relating its thermal energy in this case. So if air is allowed to expand, the temperature goes down. And that's true for all gas. We can look at the opposite situation. What if we force the air to compress? Air isn't going to compress on its own. We have to force it down. So if we force it down, then we're the ones doing the work on the gas. And that means we're adding the energy to the gas. So in that case, the gas temperature goes up if it is compressed. All right, try this question. It's a little different. I should mention that this question is often missed. This is one of those common misconception questions. The answer is white. The white surface will be warmer at midnight on a starry night. So we should go through that. If you got this wrong, you'll want to pay attention to this next part. To fully explain that question, we need to discuss a different form of heat transfer. So read this question and see if you can pick out which form I'm talking about. Well, whether by process of elimination or just prior knowledge, we're talking about radiation. So radiation does not need a medium. A medium is a material that it can move through, like air would be a material. Sound needs a medium to travel. You can't hear in space. You've heard that phrase before. Light or radiation does not need a medium, so radiation can travel through the vacuum of space just fine. Radiation in general, we're going to call it heat transfer by the emission and absorption of electromagnetic waves. I want to point out here that I'm not talking about nuclear radiation, which is little particles being ejected from the nucleus of an atom. That is a type of radiation, but in this case I'm specifically focusing on electromagnetic waves. We've talked about those before. I discussed them when we talked about why we can't see atoms, and because they're smaller than the wavelength of visible light. Well, visible light is just one example of an electromagnetic wave. There's many different types: X-rays, gamma rays, infrared. All of those are examples of electromagnetic waves. The kind I'm going to focus on most are usually represented with pictures like this. Okay, I'm going to focus on infrared radiation. For our purposes, that's the one that's most closely related to the temperature of an object. So this image was made with an infrared camera. That's a camera that's sensitive to infrared light. Visually, we are not able to detect infrared light, so we need special equipment. This is a false color image, meaning the colors represented aren't real. It was somebody's choice to represent them this way. The important part is to look at the brightest sections. So the brightest sections, like right there, over here, the amount of infrared radiation coming from an object is strongly dependent on its temperature. The higher the temperature, the more infrared radiation it's going to emit. That's why you're seeing a brighter section for the hotter areas of the dog. Let's go back to this question. Now this is a different question than I asked before, so read through it. This question's different in an important way. A lot of people get this one right because at some point in our lives we've been told by somebody that black is better at absorbing energy, or you just have experienced on a sunny day you wore a black shirt versus a white shirt and notice that the black seems to warm up more. That's because black is really good at absorbing radiated energy. In fact, true black would absorb all the radiated energy it encountered. Because it's absorbing so much energy, it's got to do something with that, so its thermal energy increases, or in other words, its temperature increases. Now this is in comparison to other colors. Other colors also absorb radiated energy, they just don't absorb the percentage that black does. So black simply takes a larger percentage for the same amount of energy that's cast upon it. It turns out that anything that is good at absorbing radiation is also good at emitting radiation. So it's taking in lots of energy, but it's also sending it out. It's re-radiating that energy. So during the day, it's absorbing a lot of sunlight, which is why its energy goes way up. But at night, because it's such a good radiator of energy, it's going to get rid of its energy faster than any other color. So even if it had more energy to start with, the rate at which it releases that energy through emitted radiation is higher, so it actually cools down faster. So what that means then is a black surface will always cool off faster compared to a white surface. The reason I mentioned this isn't to answer our current question. We've already answered that with our first observation. It's to address the earlier question when we had a black and white road surface at midnight on a starry night and wanted to know the warmer road surface. It's the white one because the white surface is slower at releasing its energy through radiation. It holds onto that energy for longer, we could say. The black surface might have started with more energy, but it emitted it through radiation at a faster rate, so it lost it quicker and thus cooled down. The white delayed that process. It hung on to it for longer by emitting at a slower rate. So radiation is a pretty interesting topic. It's very different from the convection and conduction we discussed previously. Another way to think of radiation would be to try an experiment like this. So here I just have a light bulb, and to do this experiment it's actually best if you can get one of those old-time incandescent bulbs. Those get the hottest. So what I want you to do is get a light bulb, but don't turn it on yet. Take your hand and just place it close to the light bulb, but don't touch it. So just maybe a couple inches away. And then turn the light on, and then turn it off again. So don't leave it on for very long. While it was on, you should have felt something. You should have felt sort of a warming heat while the light was on. Soon after you turn it off, though, then touch the light bulb, and you should find that the light bulb itself is not actually hot. That's an interesting effect because we're used to thinking of light bulbs as being hot, and that's why we can feel the energy when they're close. But in this case, that is clearly not happening. So why could you feel some energy when you're a few inches away, but the bulb itself isn't hot? Well, that's because of radiation. The radiation was allowed to pass through the glass. Glass is transparent to that type of radiation. So it wasn't warming the glass, but it was absorbed by your hand. Let's try some more questions. The temperature decreases. It's releasing more than it's taking in, so the net value goes down. Well, this was just a check of our previous discussion. The black pot will absorb more energy, so with more energy it will warm up faster. Another thing to consider, however, is if you want the now hot water to stay warmer for longer, keep in mind that black is also a good emitter, so it will also cool off faster when removed from the sunlight. So it really depends on what it is you're trying to accomplish. Maybe you just like black better than silver. This picture is exactly what it looks like. It's a man. He has his hand in a black garbage bag. We can't see the hand, but it is there. And that's it. There's nothing special about this picture. Until we compare it to the exact same image when taken with an infrared camera. You can see it looks very different. To an infrared camera, that bag is actually transparent, and it has no problem seeing right through it. You can clearly see his hand in the infrared, but in the visible, it's blocked. So this black plastic bag is opaque to visible light, but apparently it's transparent to infrared. We'll discuss this more at the end of the semester when we talk about why things are opaque or transparent. But it's something I just wanted to point out now. It's a fascinating demonstration of radiation. The other thing that you should notice is it looks like he's wearing sunglasses for the infrared image, but in the visible image they're clearly just regular glasses. You can see right through the glass. It turns out that glass is opaque to infrared, but it's perfectly transparent to visible. We'll talk more about these observations in a later chapter. For now, let's just look at some of these cool images that a thermal camera can give us. Here you're seeing where the water is mostly located, or was most recently located. That's the hottest part of the pot. You can see as it's coming out, it's quite hot, and it's heating up the cup as a result. Of course, it fills up from the bottom first, so that's what should warm up the quickest. You can even see the remnant of the thermal energy from when the pot was actually in contact with the table. I really like this one. It's obviously a spider in somebody's hand. There's nothing special about the spider to make it look this way. That's just the way they look in an infrared camera. You've probably heard the term cold-blooded. Spiders are cold-blooded in the sense that they're not producing their own internal energy. They don't regulate their body temperature. They're not attracted to warmth. They're biologically structured to not shiver like we do. It's almost like antifreeze in their veins. They're designed not to necessarily freeze, but as it gets cold, they'll become less and less active. Now, they certainly can eventually die if it gets too cold, but very different biology than us. This last image is really a summation of all three of these heat transfer mechanisms. Here, when you're warming a pot of water by the fire, the pot itself obviously has convection. The liquid closest to the bottom heats first, which warms it up and causes it to rise. The cooler liquid sinks, and then you get these convection currents, this cycle of moving water that's known as convection. Of course, the handle itself should be warming up. That's conduction, and it can eventually pass into your hand, so it's good to choose some sort of material that has a very low conductivity, so the energy transfer is very slow. And then down here on the side of the fire, coming out all around the fire, is radiation energy. This also leads me to one last interesting experiment you can try. The next time you're by a campfire, really just any open flame, try holding your hand to the side of the flame. And start from the outside and kind of move inward, and you'll find that you can actually get pretty close to the flame without it being uncomfortable if you go in from the side. If you tried the same thing from the top, you'll find that it's much more uncomfortable further away from the flame. In fact, if you try to get the same distance from above as you did on the side, you'll definitely burn your hand. So why is that? Why can you get so much closer on the side than you can right above? Well, how would you answer that? Let's go through this. So the flame itself is in contact with air, and so it's rapidly heating the air that's in contact with it. That heated air is, of course, going to rise. That's what we call convection. On the side of the fire, all we have as far as heat transfer is radiation. Turns out that convection is actually much more efficient at transferring energy than radiation. So you're getting a lot more energy coming at you through convection than you are through radiation. So the distances that you can approach are significantly different. Now, if you're smart enough to actually stick your hand in the fire, you'll get a first-hand experience for conduction, but please don't do it on my account. That wraps up our discussion of 3 types of energy transfer mechanisms: conduction, convection, and radiation. This is also as far as we're going to go with the material from chapter 16.